and almost it has been 70 years of working research that I've been doing. So let's dive into the presentation. So let's briefly discuss about the content. We'll talk about geospatial technologies. I'm hoping that by now you must have got some ideas about what is remote sensing, then what is geographical information system or GIS, then global very commonly and very fondly called GPS. Okay, so we're going to talk about a little bit about how you called geospatial technologies, of course, and then we are going to talk about climate change and what is going on in terms of agriculture, and we are going to look at some of the background of climate change in the agriculture, how these related, and what is you gather information, and that's why it's called remote from remotely. Okay, it's not the. I mean, obviously, if you talk about TV remote, you turn on your TV remote from a distance. You're not going to touch the button. So it's basically similar thing. You're taking information. You're doing something from a distance, and how it is done. Why we are saying that without coming into context, we can gather information. It's because of this reflected and emitted radiations from objects. So any object, it's a very basic principle of physics that any object which is above absolute zero, it's emitting or radiating energy. And those energy wavelengths in different wavelengths are captured by the sensors. And these sensors can be camera, radiometers, and any other which are in which can sense these energies. Okay, and then these energies are recorded, and as you can see, uh, this sketch that what is happening. Um, so the most of the energy that we are talking about comes from sun. Okay, and it enters our atmosphere, and then it strikes all the objects which is possible, which are possibly present on the surface of the earth, and then it's reflected back, and those reflected or emitted radiations are recorded by various sensors. Like here I have shown a satellite, and these radiations are being recorded on satellite, and then satellite sends those data, those information in the form of image or signals back to us or at the centers where we can process this data. Okay, so this is the first component. Then the second component is Geographic Information System, GIS. Okay, these are all independent systems, but when we are talking about uh, applying these systems, or when we are talking about geospatial technologies, then they all are integrated together. Okay, so, so that's why we just use a common term called geospatial technologies. So the next component of geospatial technology is Geographic Information System, and again, I believe that by now you must have learned something about GIS as well, and you must have known that the data types, different data types that GIS utilizes, or the structure, data structure has three common type, most common type of data. There could be some other different types, but these three are the most fundamental data types. So the first one is point, the second one is line, and the third one is polygons. And what do we do with these data types? Uh, so imagine that we have, Earth surface, and then there are various objects on the surface of the Earth, and those features, objects, landscapes are represented in these forms, either by points, by lines, or by polygons in this system, which is called geographic information system. For example, we'll start with points. Okay, points we would represent just locations. Okay, when we are not interested in knowing the area or the length or any measurement, when we are just interested in knowing the location, exact location, then we use points. Okay, then lines, of course, when we are interested in going from one direction to another, or when we are interested in knowing the length, then lines we would use to represent entities like roads, rivers, and other linear features. Okay, and then polygons, then the third data type, polygons, and these are basically boundaries, or these are these data types are used when we are interested in knowing the area, okay, or the parameter of a of an object, okay, of a building, of a park, or even of a district or a city. When we are interested in knowing the entire area, okay, so then we use boundaries. All right, and when we combine all these from the beginning, then we can model the Earth surface. Okay, then we can prepare a 3D model or a 2D model, or basically a digitized model of Earth surface and various objects in our computer in through a software. Okay, I think people are still entering, so I hope Gaikwad sir, you are admitting them, because at times when I'm talking, I may forget them to let them in. So please see if somebody is waiting. You can always tell me. Okay,
Yes,
so
sir.
third component. Thank you. Thank you. So the third component of this geospatial technology is called Global Navigation Satellite System (GNSS). Commonly, it's also called GPS. Although GPS itself it's a type of GNSS. Okay, and since we have been using GPS for I think forever. I mean, as far as I remember, this used to be one of the foremost GNSS services that we used, and still we are using in our phones and everywhere. So that's why it's very commonly called GPS, and it's a satellite-based navigation system, and that is used for locating positions anywhere on Earth's surface. Who designed it? It was the U.S. Department of Defense, and it consists of satellites, control, monitor stations, and receivers. Okay, and that is how, I mean, I'm showing it with the help of an animation that satellites, these GPS satellites, they send signals, or the GNSS satellite, they send signal, they strike an object, and those signals are sent back to the satellite, and the time delay, okay, in sending and receiving the satellite, the signals from the satellite is calculated by the satellite itself, and then we can get the location based on that. Okay, so we can know the exact location on the Earth's surface. Okay, so what data can we get from this global navigation satellite system? As I said, location. The main thing is location, and I've prepared a map just to show you. This is one of the part of our university, Shuart, and this map was prepared by one of our some of our PG students, master students of remote sensing in GIS. So they took various location points through their GPS, and in the background you can see that's a satellite image. And when they were taking locations, they were also mentioning, or they were also putting down the name of that location, what is there on that location. There could be hostels, there could be library, there could be some buildings, playground, and that data is entered into the software, either QGIS or ArcGIS, and then you can create such maps. And these maps are always useful because you are looking at a very large area on just on your computer screen. Okay, and you can plan, you can design things in a different way rather than just seeing them from the front look. Okay, so it's always, when you are planning, when you are designing things, it's always good to have a top view. Okay, because in engineering, or in designing, you need all views. Okay, the front view, the side view, the top view, and this is the best view that you can get through these technologies. Okay, the satellite image comes from remote sensing. Okay, the location comes from GPS or GNSS, and then when you combine them in a GIS environment, you are using a GIS software, Geographical Information System. So it's all integrated together. Okay, so we'll just talk about some of the things that we can done through geospatial technologies, or some of the advantages. Uh, the first advantage we have already seen in the previous slide, that we can map large areas. Okay, the areas where we have to spend a lot of time visiting, through maps, through which are built through these technologies, we can view just sitting in our office, like something like Google Earth. I think most of you by now have been using Google Earth. You can see various features, you can get information about various locations, various objects, just by sitting in your office on your computer screen, or even through your mobile. Okay, so that's great. It's one of the very useful example of using geospatial technologies, mapping large areas. Then it provides spatial information, not special, but spatial. What is spatial? Information which is distributed in space. So we are not talking about just a particular location or just one thing, but we are looking at the entire extent of the area. Okay. For example, a typical satellite images coming from Landsat. Landsat is also a constellation of various satellites which are providing you imagery of Earth. Um, one image covers around an area of 180 square kilometers. Okay, it's the spatial information. Okay, in a single photograph, you can see so many things at the same time. Okay, so that's spatial information. Then again, one of the strengths of these technologies is a retrospective view. Now, what is retrospective view? Retrospective view is, one thing is that you take a satellite image, maybe for today, and that's almost near real time. Okay. Another thing is, if you want to take a satellite image which has been taken 10 years ago and compare that. So that's your retrospective view. You can go back into the history, because satellites have been recording images for maybe almost 30, 40 years ago. I'm pretty sure you can get a Landsat image in 1980s. Okay, so you can go as far as like 40 years ago, and you can see change. What are the changes? So one of the uh, very important component of or application of geospatial technology is in change detection. What happened 10 years ago? What happened 15 years ago? So that you can plan the future in a better way, or in a efficient way. Okay. Apart from retrospective view, we can also do near real-time monitoring. I mean, the satellite will come at, for example, at 10 a.m. in your area. It will take a picture, and most likely in a matter of couple of hours, you can get that image. Okay, so that's almost near real time. And of course, if you are flying your own drone, you are taking images in almost real time. Okay, so not only going back into the history, but also current, what's going on right now, you can monitor. Okay, and based on history, based on present time, you can make, you can use models to predict futures, to do future predictions. Okay, so it's taking all the three components of the time: past, present, and future. What else do you need? Yes, you need something like X-ray vision. Okay, when we have to diagnose something, when we have to see something which is not visible through our eyes, we need some extra information. We need some tool that can help. And X-ray vision of geospatial technologies helps a lot. And this is a very small example that I would like to share with you. Uh, Agriculture field, it looks green through our naked eye, and we can say that everything looks good. But um, if we would like to see like really what is going on in this field, is everything is really okay, then we need an X-ray vision. So this is what you get through a satellite image. In It can be in a thermal band. I think you must have known by now what is a thermal band, or even a vegetation index, or a near infrared image. Okay, we'll talk about this a little bit in the further slides. But just to tell you in very simple word, this image is of the same field. Okay, at the same time. Okay, but this is a true color image, what you see through your eyes, and this is something through the satellite. Okay, satellite imaging in a specific band. Okay, and all these red, yellow spots, something is not going fine. Okay, there could be some stresses in the crop. Green area is good, green area is fine, but the red and yellow spots or area, um, most likely some stress is occurring. But the good thing is that you have known it prior to a permanent change or a permanent damage. Okay, the permanent damage is when the color changes, when the vegetation or the crop color changes to light brown or something like that in a full growing period. When you can see the color change through your eyes, that's something where the permanent damage has happened. Okay, so in order to avoid that permanent damage, you need to have a monitoring system. Okay, and if you can monitor the stresses like we are seeing in this image at the onset, in the beginning itself, then you can do something. You can go to your field, you can see what's going on, and there are most likely common issues like maybe the irrigation is not reaching in these corners or in these spots, or maybe fertilizer that we are using, it's not being applied uniformly in the field, or things like that. Only some common problems. Okay, and once they are fixed, you can get a healthy crop and you can get a maximum yield. Okay, so this is one of the strengths of geospatial technologies, remote sensing data. All right, let's move on. And various systems are there for information, for taking information, but I'm just going to talk about some of the very common systems that are mounted on satellites, that are mounted on drone, how to get the data. This is just a very brief overview of those data. Most of them are cameras. Okay, and you have obviously a natural camera. That's your first remote sensing camera, a natural color camera, which is RGB. Okay, red, green, and blue camera. Okay, so RGB is a true color or a natural color camera, and it's called visible light payload. Then, if you want an X-ray vision type of a thing, then you would go with infrared payload. Okay, that you cannot see through your eyes, but once the image is taken and it'll look still a black and white or a grayscale image. But when you start giving it colors, then you can analyze it. Okay, then we have radar, SAR payload. Then there comes multispectral. Multispectral means there are multiple bands. Okay, multiple bands or in a single image. They are combined all together. And then, of course, hyperspectral. So within a single band, there could be multiple bands. Okay. So multispectral is like, 4, 5, or 6 bands. Hyperspectral is multiple bands, more than you can say 50, 60, or even 100 bands. Okay. And these are used specifically for a particular disease detection. I mean, if you want to go beyond just stress detection, if you want to go what type of stress it is, what type of a disease it is, then hyperspectral payload. Okay, and then of course, this is newer technology, LiDAR. not like new, but newer. Uh, uh, it has been also used for many years, but from rest of the technology, this is a newer technology that gives you a 3D model of a surface. So it is used to create elevation data. Okay, in simple words. All right. So it has a long history, as we are seeing, geospatial technologies. And I'll just give a brief introduction where I started in 2003, where this was the first time when I started using these technologies. And then I got interested. And why not? Because this was the first exposure for me. This was a small plane, a 6-seater plane, and where the camera system was mounted. Okay, that we have talked about these camera systems. And I used to fly in this plane. I was not flying the plane, of course, but I used to fly in this plane and take imagery. So let's look inside this plane. This is the inside of the plane. Okay, and in those times, in 2000, in year 2003, drones are not very popular. They were still evolving, so we didn't had a drone. So my advisor or my teacher there, he assembled the system, and uh, it again, I mean, it's a great example of geospatial technologies. Okay, so you can see these small screens. These are all cameras, different cameras. Okay, and this is a thermal scanner. You can get thermal images. And this laptop that you are seeing, why I'm looking at this laptop, because this is connected to the plane navigation system, and I can see the plane, how the plane is flying in our area of interest where we are capturing images. Okay, and so it was fun. It was a great learning experience. And something that I was doing at that time was this image. I was taking all these types of images. What are these images? These are images in near infrared band, in single band. And this is a photograph of a potato field. So in US they used to have a circular potato fields. Okay, and their farmer association, they hired us. They would like to see images of their field in the uh, throughout the growing season, 2 or 3 times throughout the growing season, so they can identify these types of spots. Okay, what's going on in their field. This is a huge field. This is almost a the diameter of this field is almost, you can say, almost about mm, just less than a kilometer, 1 kilometer, almost 1 kilometer, the diameter of this field. So huge field. So it's practically impossible to, if you have like 20, 30 feet, it's practically impossible to go and check all the time. So this was the easiest way for them to just look at the photograph. And since this image had geocoding in it, geocoding means location information, they can just spot these areas of non-uniform growth, these gray and black and shaded areas, and they can go in these areas directly to see what was happening. And from their experience, what we learned was that these are all common problems, like irrigation is not reaching, fertilizer application issues, or even some pests that might have just started in the crop. So they can be stopped at that time, then and there itself, and they can have a good yield. Okay. So again, technology. We come to application parts. There are several applications of these geospatial technologies. I have just named few just to show you examples. Uh, One of the most common application is in surveying and mapping. Then one of the most important application is in agriculture, environmental protection, then delivery, transportation, meteorology, forestry, all those. It's yeah, you name it, it has in wildlife management, in ecology. Um, you name it, there is an application. These are just few applications, but today we are focusing on climate change and agriculture. Okay, so we are going to talk about those applications. All right. So we'll just discuss some background. We'll look at the background of climate change. So, and what does it do with agriculture? Okay. So it has both direct and indirect effects on agriculture productivity. How? Because because of the climate change happening, there could be changes in rainfall pattern, onset of the droughts, flooding. These are extremes. Okay. And then geographical redistribution of pests and diseases. Okay. So this is something which will always hamper the agriculture. Okay. And especially though that agriculture which is dependent on a rainfall. Okay. Rain-fed agriculture. Because when the rainfall patterns are changing, it becomes very hard because there are many farmers, okay, around the world, and especially in India, which are dependent on rainfall, which have lesser means of their own irrigation system. Okay, so when climate change is going on and this is happening, we can see uneven distribution of rainfall, and we can see extreme climatic events like drought and flooding, and this is all affecting agriculture productivity. And if we don't act now, then it will be a problem. So the response should be now to feed our future generations tomorrow. Okay, so it's very, very critical, and all the scientists, I think, they are focusing on how we can sustain our agriculture, how we can make our agriculture profitable in changing climate times. Okay, when the climate change is happening, what we can do, how we can survive, how we can, you know, make more efficient growth, or how we can reach the potential yield. So all these challenges are there, and I would also like to show you some briefs out of FAO report. So FAO is the Food and Agriculture Organization of UN. That's the premier organization of uh, which lays the guidelines of food and agriculture all over the world. So this increase in risk of extreme weather that we have talking about, like changing rainfall patterns, floods, droughts, this is a problem. Okay, this increases pressure on agriculture production as crop growth and yield are highly sensitive to climate conditions. We all know that. Okay, and it increases the water shortage. There is a scarcity, and obviously, when water shortage is there, this is the single most effective parameter, water shortage, which can hamper or which can negatively affect the agriculture production. Okay, because if you are not giving proper irrigation, the yield will be low, or yield is related to agriculture, crop yield. Okay, irrigation is related to yield, and we'll see in upcoming slides how. So, what needs to be done? Okay, there has to be some transformation. There needs to be something that can by that we can achieve food security. Okay, and FAO has been giving various guidelines. I think many of us should know by now what are those guidelines. Okay, and what are those adaptive measures, what are those tools that help us to sustain our agriculture productivity in changing climate times. Okay, so in changing climate. Okay, the three main objective of this climate smart agriculture is sustainably increasing agriculture productivity and income. Okay, adapting and building resilience to climate change, and then reducing or removing the greenhouse gas emissions wherever possible. Okay, So we will be interested in what it can do or what we can do with our agriculture in changing climate times. Okay. And as we have already talked about the climate smart agriculture, it's developing strategies to secure sustainable food security under climate change. Okay. It also helps to provide stakeholders from local to national, international levels to identify agriculture strategies suitable to their local conditions. So not one strategy is mentioned because the region changes, the climate changes, the weather changes, the crop variety changes. There's so many changes, so not one strategy can be applicable to all. So it has to be region one. Okay. So they have suggested some practices like integrated practices. Okay. First of all, the motive is to have greater efficiency in use of the resources, okay, and more sustainable management of natural and human created processes in landscape. So again, I mean, these are some of the text that I have noted down, but the things that we can remember, okay, is the efficiency in use of our resources. Resources like water, okay, it will be going to be a challenge for us, and I'm going to show you some facts about the water availability as well because of the changing climate. Then next is focus on crop production to cope up with the challenge of climate change. Okay, because climate change is disturbing the natural cycle of agriculture, and once the natural cycle of agriculture is disturbed, okay, the entire economy of a country can come down. Okay, especially a country like India, which is fully dependent on agriculture. Okay, we do have industries, we do have businesses, but we are an agriculture-oriented country. And the countries who have a very strong agriculture, they are becoming developed, or they are already developed countries. Okay, so we need to just advertise these use of technologies in agriculture. Otherwise, we will be behind of many countries. Okay, so we need to ensure that we use good technology, and we should maximize our efficiency, maximize our use of resource, because right now we are not, I think, putting more focus on proper water use, and once this water becomes limited, then it will be a problem. And this land and water management is one of the key elements of climate smart agriculture. Okay, and we have to focus on, we have to manage all the water resources that we are using, and especially the agriculture sector, because agriculture sector is one of the largest consumer of water. So we need to be very sure, okay, to use it wisely, to use it with some knowledge, okay, to cope up with the climate change, as well as to maintain our resources, to utilize our resources in a best possible manner. These are some of the facts. So right now we'll talk about, so we have two types of crop productions, or two types of agriculture that we can divide on base of water use. Okay, so 20% is of irrigated agriculture. Okay, and 80% is based, it's dependent on rainfall. Okay, now climate change is happening, everybody is doing their part, but there are things which we cannot control. Okay, which we cannot control, environmental factors. Okay, we can do our best, we can do our part, but still these rainfall patterns and all these things, they cannot be controlled fully. Okay, so where we can focus is on this 20%, which is irrigated. Irrigated means we are supplying water to them, okay, through our different resources, through our rivers or lakes or groundwater. Okay, so we need to focus, we need to maximize on these 20%, because this contributes to 40% of the total food produced worldwide. Okay, so only 20% of irrigated agriculture contributes 40% of the total food product used worldwide. So these are World Bank facts. I have not written these. These are World Bank facts, and everybody knows who is World Bank. Okay, so this is very critical. Okay, 20% of irrigated agriculture is contributing 40% of total food produced worldwide, and rest 60% of total food produced is coming from 80% of agriculture, which is based on rainfall. So, you see the importance of this 20% agriculture, irrigated agriculture. Okay. And there is something that we can do about it, because irrigated agriculture on an average is at least twice as productive per unit land as rainfed area. So we can increase the productivity, almost double the productivity. Right now, for example, it is 40% of total food. We can go up to 80% of total food. Okay. There's huge scope, huge scope. Okay. And this is the way to go in changing climate, because when the climate is changing, again, we are doing everything. I think all the organizations are putting a lot of effort, but still, environment, climate, this is something that not everything can be controlled. Not all things can be controlled. Okay. I think people are still joining the meeting. So what we can do? We can allow more production, intensification, and crop diversification. Currently, now here comes the water. Currently, agriculture accounts for almost 70% of all fresh water withdrawals globally, and even higher share of consumptive water use due to evapotranspiration of crops. So, here is something that we can focus on. 70% of all fresh water withdrawal. So we need to be very specific, very particular how we are maintaining our agriculture, how we are irrigating our agriculture, because we are using 70% of fresh water in agricultural use. Okay. And we don't have a choice, because due to population growth, urbanization, these are two other factors apart from climate change. The competition for water resource is expected to increase, and obviously the compromise will be done on agriculture. Okay. Population is expected to increase to over 10 billion by 2050 in next 30 years. We are not looking far ahead into future. We are just looking like 20, 30 years after. Where urban or rural, but this population will need food and fiber. If we don't act now, that will be a chaos. Okay. And that agriculture production will need to expand by approximately 70%. Okay. So these are some of the very hard facts. Whatever agriculture we have now, we have to increase it by 70%. Okay. In these times of climate change. So what is the need of the hour? Let's come to the main thing. Okay. We have learned some facts. We have seen concerns in terms of climate change and agriculture. Now, what needs to be done? Okay. First of all, produce more with optimal use of resources. Okay. We have to increase our production yield. And how we can do it? By proper crop health monitoring. Like, we cannot afford that crop will produce less because of disease, pest, and because they are not managed initially when we could have managed them initially. Okay, when we waited too long, then the crops are affected. And then what else we can do is irrigation management and mapping. Whatever water we are using, we need to manage it properly. We need to map, and I'll show you what does it mean by mapping. Okay, we should know how much water the crop is using. Okay, and of course, increase in water efficiency. So we'll talk about more in later slides. What is water use efficiency? Some of you might already know it, but in simple words, it's more crop per drop. I think all the political parties, even our PM, is talking about this term: more crop per drop of water. Okay, it's not only water, but any resource, fertilizer or anything. Okay, and of course, do these things: crop health monitoring, irrigation management and mapping, For increasing water use efficiency, we need technology and information. We need more technology and information that we have right now, so that we can plan in a better way. We can act. We can do some actions. Okay. So I'm going to show you now some of the applications, and these are basically some of my work that I did for uh, Prayagraj. Right now, it's called Prayagraj. The previous name was Allahabad. That you must have heard about this city. Okay, and it's a district in the state of Uttar Pradesh. So I did previously some work, and I'm going to show you some of the examples from that from those work, that how I have applied geospatial technologies and what were the outcomes. Okay, what we can do with these geospatial technology in terms of climate change and agriculture. Okay, so the first thing that we talked about was to cope up with climate change and its impact on agriculture. We need to monitor crop health because of these extreme events, and we have already seen in our initial slides the extreme events can have an impact on the growth, can put crops under stress. There could be some pest and disease which we may have not seen before, but right now they are occurring in the crops. All such type of things. Okay, and we need to know them at the onset, in the beginning itself, because if we don't see them in the beginning itself, then it becomes late, and if it becomes late, then the changes are irreversible. We cannot change the damage. The damage has already been done, and then it will be a problem. Okay, so as we know that agriculture production gets hampered by stresses induced in crops during various stages of growth due to environment and management related issues. Okay, environment is again climate change. Management is us. If we are not putting focus on it, if we are not monitoring it well, or if we have, you know, lagged somewhere, then this could happen. And there are several uh, reasons why these stresses are happening in the crop. Like management related issues are irrigation, nutrient deficiencies. Environment related issues are diseases, where diseases that can occur, infestation. Okay, various pests can attack the crop, and this is again because of environment, changing climate. Okay, what is needed? Continuous and consistent monitoring. Okay, we need a continuous and consistent monitoring, and this helps to take remedial action even before the damage is irreversible. This is the main objective for crop health monitoring. We have to monitor crop, and we have to do before the damage is permanent. Okay, how we can do that? There is one option. It's called a vegetation indices, VI. Okay, and one of the most common VI or vegetation indices, normalized difference vegetation index, NDVI. Okay, that can be estimated from satellite image. It's based on the ratio of reflectance values of crops in visible and near infrared region. Okay, and this is a typical pattern of NDVI uh, for surfaces. I mean, obviously the range. It's an index, so there is a range, there is a scale, and the scale varies from -1 to maximum value of 1. All the negative values below 0 are water surfaces. Okay, and above 0 are the non-water surfaces. Okay, and as we go in region of zero point 0.6, zero point 0.5, zero point 0.6, zero point 0.7, it shows us the health of vegetation. Okay, and this is a typical graph of NDVI in terms of days after sowing the crop. Okay, and as the crop grows, the NDVI will also increase, and it will reach a maximum point. And after that, what is happening? It falls off because now the crop is drying. As still the crop is green, it's good. As soon as it changes its color because of maturation, because they are getting ready for harvesting. So that means the NDVI will also fall. But if the NDVI is falling somewhere here, then there is a problem. Okay, it should continue to increase throughout the growing period till the crop is at its peak, and after that the crop will dry because it's getting ready for harvesting. So this is a very good tool, NDVI or vegetation index, and the crop health can be monitored. Okay, this is a well-established uh, vegetation index. We'll look more about it, like what's happening. Okay, it is widely used for agriculture mapping and monitoring. Okay, and since what I mentioned before was that we are using two bands, and these two bands are near infrared and visible bands. Okay, and these two bands uh, gives us an idea about the health of the plant. Okay, because these two bands, especially the near infrared band, is sensitive to the chlorophyll present in the leaves. Okay, and as I've already mentioned, it's obtained or developed directly from the multispectral satellite images. And NDVI is something which can be obtained throughout the growing season to detect the problem with the health issues. Okay, and we have already seen it's based on reflectance values of various features like crops, vegetation, soil, water, any other impervious surfaces in the visible and near infrared region. Okay, so just to let you know the formula, this is the formula that NDVI equals to near infrared band minus red band divided by near infrared band and red band, and these two bands you get from satellite images. Okay, in you can put it in a spatial modeler in a software where you are using it, and you can run this in this, and you get that. Okay, based on the values, you can identify where in which field there could be a problem. Okay, I'm going to let these three people enter. They are entering, keep entering all the time. Let's enter that. So as you can see in this picture, that a healthy crop or a healthy vegetation is having an NDVI of around zero point 0.7, and an unhealthy vegetation or a drying vegetation whose leaves are brown, or the chlorophyll amount is decreased, it's having a very low NDVI value. Okay, so this low NDVI value can be related to low chlorophyll presence. And low chlorophyll means if it's during the growing season, then it's a problem. But if it's later in the season when the crop is almost dry and ready to be harvested, then it's fine. So it gives you an idea, right? It gives you an idea health of the crop. Okay, let's move on. So I have shown you a graph where different values, okay, can be seen. For example, bare soil is at the lowest end of the NDVI scale. This is the NDVI scale. The values are ranging again. We are talking about non-water surfaces. So zero point 0.1 to zero point 0.8. Okay. So this is bare soil. And then, there is an overlap between bare soil and urban areas at the lower end, because at the lower end, urban areas can be fully urbanized. There is there is nothing like vegetation here. But as you move on, you come to point 2, point 3, then there is a threshold. Okay, this threshold, right after this threshold, our vegetation starts. But there is again some overlap because the vegetation can be totally dry or very sparse. Okay, so because of the sparse vegetation or because of the dry vegetation, the values can be very low, and in a similar way, in urbanized area there could be some vegetation present. Okay, but again it can be in a poor health condition or almost dry. So that's why you can see some overlap at the higher end of the urban area values of NDVI and in the lower end values of vegetated area. But as you go beyond point 3, the health or the vegetation intensity increases. The higher values will tell you that the vegetation is healthy or the intensity it's good. Okay, it's not very sparse or dry vegetation. So that's good. Okay, let's move on to next slide. And we will see in pictures just to give you more idea about this NDVI because NDVI is it's a really important or a key parameter to monitor crop health. Okay, so if I have to give you just a range, so point from 0 to point 2, it's almost bare, and then again, urban areas is also point uh, up to point 2 or even point 3. It can go up to point 3, and then medium vegetation here in this third photograph, it's from point 2 to point 4. Okay, medium vegetation means um, it's not dense. There are patches in between, and it's not maybe it's not very healthy vegetation. Okay, so that's why I have put it in this range, point 2 to point 4. But again, I mean, as you process the images, as you will develop these NDVIs, you will get more ideas. So this is just for a reference purposes. And then NDVI, which is greater than zero point 0.4, it is indicating good, healthy, and dense vegetation. Okay, with a full cover. Okay, so that's good, and that's you can take as references. But again, not exact values. Values will change. So in this example, I'm going to show you NDPI maps that I have developed for 2015 and 16 wheat growing season in Allahabad district. Why 2015 and 16? Why I'm saying 2015-16? Because normally wheat is grown in winter season, and it goes from November, December to January, February, March, April, and sometime in April, late April, the harvest happens. Okay, so here I took 5 satellite images every month, one satellite image every month from December 2015, January 2016, February 2016, March 2016, and April 2016. Okay, one each month. Okay, these are 5 satellite images. And if you would see, I created these maps and I have put it in a form of animation so that you can get a sense of idea. If you remember in the some of the beginning slides of NDVI, I showed you how the graph or the NDVI value is increasing and then it starts decreasing. Okay, and you can see by the colors, green color is vegetation and yellow and brown is when there is some problem or the vegetation is drying off. So it starts from December. Okay, it's a little bit yellowish. Then as the season progresses, it becomes greener, greener, greener. And I believe in the March and April, it becomes brown on the brown side. Okay, and you can see I have given a scale of maximum zero point 0.8. So all the values throughout the growing season, as they are increasing, they would increase, they would approach to the maximum value zero point 0.8. At that time, if some of the values are less than zero point 0.8 or even less than in the lower region, maybe zero point 0.4, 0.3, 0.5, it's not good. Okay, so you can see the entire progression of NDPI throughout the wheat growing season. Okay, and it's a good piece of information because when you get um, these types of data, you can make decisions, you can act, you can see like what can be done. Okay, and for that you need, of course, information. Okay, and this is doable. You can do it. Okay, and The strength of such type of analysis is not only maps. Maps are, of course, one of the biggest strength where you can see everything in, in a picture. But then what that picture says, you need to have some data. The good thing about geospatial analysis is that you can extract the data from these satellite images. So I used like 100 wheat fields and I extracted their average NDVI value. And I have put it on this graph. So these trends are the average NDVI values of 100 fields. So on each month, okay. So this is in December, and we can see that the maximum NDVI value is zero point 0.2. Okay, so it's varying from 0 to zero point 0.2, and most of the fields are here in this region. Okay, zero point 0.1. So that means the crop is have just been planted. I mean, it has just started growing. Okay, so it means that most of the fields are in the region of zero point 0.1. Now in January, so from December to January, we would expect some growth in the crop. Okay, and that growth we can see here that the values from zero point 0.1 is increasing and moving to up to 0.7. Okay, point. Most of the these are the half of the fields are above zero point 0.4, half of the fields are 0.4. So this could be a problem, okay, because we would like to see more what happening here. And the same variability we are seeing in February image also, where we would expect that most of our fields will have a higher value. We have large number of fields, all the median has increased that now we have at zero point 0.5. So NDVI at 0.5 median means half of the field are beyond zero point 0.5, but still half of the field which are below zero point 0.5, those are problematic. Ultimately, it's going to affect their health and yield. Okay, because if you see the next image in March, now the crop is on the process of drying, or they have reached its peak growth. Now they are drying and getting ready for harvesting, and that's why the median value will come low, and it will come further low in April. It's almost mid of April, where it's almost ready to be harvested. The temperature is very hot, and it has to be harvested before it can totally gets dried off. Okay, all right. So that was we talked about the variability in the fields. You know, different fields. We have taken 100 fields. Now the again, I'm showing the level of information that you can get. This was the overview, the overall picture at a district level. These names, sorry, I forgot to mention. This is the Allahabad district, the entire district, and these subdivisions are the tehsils, okay, or subdivisions of a district. Okay, Bara, Karchana, Meja, Korau, Handia, Phulpur, Solang, and even Allahabad itself, it's a tehsil also within the Allahabad district. So that was an overview, or it's called a bird's eye view or a district view, and this is individual fields view. You know, if you want to see the variability or and the next level of information that you can get is within a specific field. What's going on within a specific field? For example, this field, okay, and you see that there are areas red color which are not very healthy. Then blue color looks okay, but again these red colors are not very healthy. So from district level to fields level, multiple fields level, now from multiple field level to single field level, we can go up to this level and we can see. So I took one sample field from this TESI and just check what is going on. So here we can see that the growth is sorry, fine, and most of them are on the higher side. But here the growth is all variable, okay, because of this pattern. Some are high, but some are low on the lowest side. So this is something which is not good because we need uniformity like this. This is lots of variability. This is uniformity, this is variability. And we don't need variability. We need uniformity. Like entire field should have a good uniformity. Now, this was about the crop health. The next component which we need to focus on on our agriculture part because of climate change, because of limited resources, or because of limited water resources, is something which is called crop water requirement. I'm not going to go in deep in it, but see, in simple words, we all understand how much we should irrigate, how much we should put water into crop so that their health is optimal. It should equal to the amount which is being lost by the crop itself to the process of transpiration. And we are also including a component called evaporation because within crops there will be always surfaces where um, exposed surfaces where evaporation is taking place. So it's called evapotranspiration. But as the growing season continues, the evaporation component becomes minimum and the transpiration component becomes maximum, or that's the majority of water loss through transpiration. So we need to supply that much amount of water to the crop. Okay, so E component is the soil surface by evaporation plus crop transpiration. Okay, and when we are combining these two, it becomes an evapotranspiration. So this is one of the most important and critical parameter in crop production. Okay, apart from your fertilizers, apart from nutrients, apart from other practices, first and foremost thing is proper irrigation. And irrigation will depend on the amount of ET or evapotranspiration. So what we can do through these techniques or technologies or geospatial technologies, we can see irrigation application, we can monitor the application, we can manage the irrigation application. Okay. So again, this map was created for the Allahabad district. Okay. I created this map and this is showing the water use of crops in various uh, tehsils of Allahabad district. Okay. And if we have to pull out the data just to see what's going on, so we can see that how varied the crop is using the water. Okay, so between this is ETA, so this is evapotranspiration, and it is in millimeters. Okay, in depth. If you multiply by area, it becomes volume. Okay, and that's how. Excuse That's how the water is supplied to the fields. But here the main problem that we are looking is that areas like Sorao, Phulpur, it's okay, but these brown patches, these areas, these are giving non-uniform water use. And there are areas which the fields are not obviously not being irrigated properly, and that's why they are showing the less water use in this area. Okay, and when they are not irrigated properly, ultimately it's going to affect their yield. So it's very interesting. I'm going to show you how it's affecting their yield. So let's move on. And this is the field view. If you look at the group of fields, okay, some fields are, this is a true color image, or this is how you see with your eyes, like some fields are really green, but some fields are not as green as they should be at this time of period. Okay, and you can see in there water use, why that's happening in there, how they are using water, how they are irrigating. So here we are monitoring how much water they are being applied or they are being supplied. And if they are not being supplied good water, we can see that they are almost like light green and there are patches of yellowish in color. And these areas will be problem. These are going to lower down the overall crop production. Okay, these are individual fields that we can see. Okay, this is just a view of group of fields. Blue fields, they have been recently irrigated, so they are showing high water use. Green fields, they are well irrigated, so they are almost healthy. But our concern is these patches. In many fields, we are seeing these patches here. All these patches are problematic. They are going to create problems later on in the ultimate yield of these fields. So these types of technology or information that we can get will help us to map what is going on in terms of water application, how well we are irrigating a crop. Okay, and maybe we can improve it right now, or if it's too late, maybe we can make sure that the next time we are doing it correctly. Okay, we can increase our yield in coming years. Okay, so again, when we are talking about technology, we will start looking at a district level information. Then from these images, we'll go to individual field, and then from individual group of field, we'll go within fields. Okay, and again, I have used the same example that high variability in an individual field can result these types of information. So here we see high water use areas, which is good. So most of our field, this area is high water use. For example, if I'm considering this, this area. Okay. But when I'm considering another field that is low in water use. Why low in water use? Because not enough water is being supplied. It's a highly variable supply. Okay. And again, this is going to affect ultimately the crop health and yield. And this will be a problem. So we have talked about the crop health. We have talked about how the water is being applied, how efficiently we are applying the water. Now comes to the ultimate question, how our yield is going to be affected. Okay. And I'll show you just with an example. This was our image of NDVI. Okay. When we were doing crop health monitoring, and it was developed for February 10th, 2016. Okay. And based on that, we are predicting yield. Okay. And the yield map, if you see, it directly correlates. Whatever the areas are brown right now and they're not as green, in the yield map also they are low yielding areas. These all areas. Okay. For example, if you look in Phulpur Tehsil, okay, Phulpur Tehsil, there are yellowish areas. Okay. When there was a peak growing season, this is peak growing season on February. Okay. But we can see some low NDVI areas. And these low NDVI areas in turn has given you low yield. Okay, we can see in the yield map. This is this is what I was talking about. If we are not focusing in the beginning, the end result will be troublesome, will be problematic. If we are not putting a focus on crop health in the beginning, our yield will be affected. All these are the effects of not proper management. Okay, let's see some more about yield. So yield estimates can be done from a standing crop. Okay, we can predict yield before the harvest. Okay, using these technologies, and we use minimal ground-based measurements. We don't need much ground-based measurement. We can predict the yield, and this is not something new that has been going on for years. It has the yield model, the most common yield model. That you can find many yield models right now in various research paper. But the premises or the background of these yield models, or the fundamental of these yield models are based on a well-researched, applied, and established relationship between a term called APAR. What is APAR? A stands for absorbed photosynthetically active radiation. Okay, so we all know that the crops, the plants, that vegetation require solar energy to do their photosynthesis. Okay, so they absorb the solar energy, the energy coming from sun. So what portion of energy they use for photosynthesis? That's called absorbed photosynthetic active radiation. So this is the term that we can estimate. Okay. Then there is another thing, this epsilon. This is called light use efficiency. Okay. Light use efficiency means how well or how efficient the plants or the crops are to absorb this radiation. Okay. Then there is another term called biomass. Biomass is estimated. It's a, you can say, a surrogate of NDVI. Okay. So it gives you crop health. Okay. And harvest index is, these are some numbers which are already published for different types of crops. Okay. So that will convert the APR, the light use efficiency, the biomass into yield. And that's how yield is predicted. That's how you can create yield maps. Okay. And you can basically see that how your yield is going to be. Okay. So we are going to see some data where we'll see that this was the tehsil-wise average yield distribution for selected fields. And we can already see that in major tehsil, the yield was highest. Okay. And the lowest was in Koraon, Allahabad, Tehsil, Karchana, Soraon. And no doubt why. If we go back and we see these tehsils, we would see in NDVI map, see, Soraon, there is lots of brown areas, Allahabad, even Karchana, we can see lots and lots of these fields which are brown in color. On screen, you may not be able to see it very clearly, but when you open this images in software, then you can see all these areas are brown, and that's why we are seeing this type of distribution. Okay, and if you look in the individual field, we have already looked into the individual field. We can see that why yield in this tehsil called media is good, because a typical field is having very less variability. And why Koraon is low on yield? Because a typical field in Koraon is having lots and lots of variability. Okay, so this variability needs to be controlled. And how it can be controlled? If we can monitor them at the beginning through NDVI or any vegetation effect. Now we come to a term called water use efficiency. When we combine the water application, when we combine our yield, when we combine our crop, all the things, it becomes one term. It's called water use efficiency. And what is water use efficiency? It's crop yield per unit volume of water applied. Okay, or it's also called crop productivity. And it's a very important term when you're talking about climate change. Okay, and its impact on agriculture, because this is what is going to be affected. Okay, crop yield per unit volume of water applied, because water is becoming scarce. Water is highly non-uniform entity. Okay, sometimes there is rainfall, sometimes it is not. So we need to focus on whatever water we have and how efficiently we can use it, and how we can increase the yield based on the water application. So that's why it's called water use efficiency. So it relates basically the water use or water applied to the yield. So we'll see in the next slide how yield is related to T, or evapotranspiration, or water use or water application. Okay. So this is the ET map that we have already seen. We have seen all the variability, all the variations, and all the features. Okay. And then if we put our yield map as a comparison, we can see similar patterns. Okay. If we are just talking about pictures, okay, the green and the blue here also you can see green area. So, excuse me, uh, when we are talking about these areas where we are applying good water, okay, or appropriate water, we are getting good yield. But the fields where you can see these brown areas where there could be stresses in the crop and possibly due to irrigation, due to fertilizer, or due to improper pest management diseases, we are not getting good yield. Okay, so this is what is happening. If we are not supplying good enough water, our yield is being affected. Same pattern. You can see same pattern. It's almost like you have developed this yield map from this map. No, this is independent. This yield map is independent. It's based on NDVI. Okay, but the pattern is similar, very similar. Okay. Now, let's see the values, how the values comparison shows up. Okay, it's same. Okay, here we are seeing the water use. The maximum water use in major tehsil, and the minimum water use is in Koram. Same. The yield is minimum in Koram and maximum in major. So the pattern is almost same. Okay, as if you are just seeing the same graph, and this proves that yield is related to parameters like irrigation, how well we are applying water. Okay? Now, so what I did was I took average water application or water use values in each tehsil. We are having how many tehsils? One, two, three, four, five, six, seven, eight tehsils, and I took an average yield of these eight tehsils. And when I plotted on XY graph, we can see there is a very high correlation, a linear correlation. Now, be careful. This doesn't mean that the more water you apply, the more yield you will get, because there will be a threshold. There will be a threshold where if you apply more water, the yield wouldn't change, or even the yield may go down because of water logging problem, because the crop doesn't need that much of water. But you have to know, or you have to understand that we have to apply optimum water. And as soon as the optimum water is there, optimum yield we will be getting. Okay, that won't be a problem. So this proves that what I was talking, what I began in the starting, जो मैं starting से कहना मान रहा था, वो यही चीज थी कि if we are not focusing on the climate change impact on our agriculture, which is the health, if the health is not monitored, if we are not taking steps in the very beginning, the crop water use will be affected. Once the crop water use is affected, the yield will be affected. Ultimately, we are getting less yield, less than potential, less than what we expect. And when we get less than what we expect, then there is problems. There is lots and lots of problems. And once there are lots and lots of problems, then there is chaos, price hikes, scarcity, and all those. So we don't want all these types of things. We need to use technology. We need to use information. We need to do actions based on or take informed decisions based on the information that we are getting from these technologies, especially during the times of climate change. Okay. So overall conclusions, what we are getting concluded here, what we have seen so far, that geospatial techniques provide an excellent mean for managing our agriculture under changing climate. Okay. Yes, I mean, of course, we are doing a lot of things for minimizing that climate change effect, but that needs to be done at a global scale. Okay, and it will take some time. Okay, when we'll see the impact of all those positive things that are being done to slow down the climate change. But before that, what we need to do is how we can sustain our agriculture. What we can do, we can do health monitoring of crops through these geospatial technologies. We can be more aware of what's going on in our crops at the very beginning. Once we are aware of the crop health at the very beginning, we can improve the health. Okay, we can take remedial actions. Okay, we can do certain things that can avoid permanent damage. Okay, we can optimize the use of inputs, for example, irrigation and fertilizer, insecticides or pesticides. We can do all these things if we have information about health of the crops. Otherwise, what we do is if the crop is healthy, we are applying fertilizer. Okay, even if the crop is healthy, we are putting all the insecticides and pesticides. It's not necessary that it should be done in each and every corner of the field. We can detect, we can use our crop health monitoring tool to see where it's actually needed. So we can optimize the utilization of such inputs. Okay. Then from standing crops, we can make some yield predictions through these technologies. And these yield predictions will help us to make informed decisions about many things. Like uh, we can also evaluate our irrigation regime, okay, or water use efficiency. And once we get hold of this water use efficiency, once we have increased, that means we have optimized our inputs, including irrigation. Okay, through using geospatial technologies, what we are getting spatial data. Spatial data, again, not spatial, but spatial data is a huge leap in information because the analysis can be done as a real-time monitoring. We can see in real time. It has been, going on forever. Like, I already showed you an example when I started in 2003. The farmers were using in the US at that time crop health monitoring tools. Okay, we can do future predictions. We can go back into the history and we can see what was happening in certain year, what was happening in certain climate condition, what was happening in certain area, and then we can compare it with our current scenario. Okay, so all these information will going to assist in better planning and informed decision making in terms of devising sustainable policies. Okay, we can devise our own policies as we have already seen that every location should have its own policy. Every area should have its own policy based on the inputs available, based on the climatic conditions, based on, of course, the cropping pattern, logistic plan. So if we are able to predict something, then we can, arrange the transportation, we can arrange the storage. We have heard stories that, all the nearby storage was full and our grain was damaged because they were lying, all those grains were lying in open. They were destroyed by rain. Okay, I think many of you must have heard those news. Okay, that so much of grain yield was destroyed because they were lying outside the storage. So we can plan that once we have information. So, you know, if you look overall at this presentation, yes, I have emphasized more on using geospatial technologies. I have emphasized the importance of using geospatial technologies, and I've shown you the importance, the result, the outcome, the information that you can get from geospatial technologies. But we have to remember one important thing that geospatial techniques or technologies they complement and supplement with the existing information network. Okay, we are not replacing the existing ground-based or any information network. We are just complementing and supplementing it. through geospatial technologies, we are trying to get additional information on top of what we already have. So we are not saying just remove every, ground-based measurements. We are not saying just remove all the information that we have for now and use geospatial technologies only. No, this is going to complement and supplement the existing information network for better outcome, for better results, for sustainable agriculture in changing climate. Okay, climate change is happening. It's going to happen. It's going on. We are doing things. I'm not sure how much these things are effective, but what we can do for now is sustain our agriculture through the technology. Okay, so we'll end this presentation here, and this is where I come from. These are different buildings. Okay, situated in my university. It's called Sam Hindenburg University, and this is the building. It's called engineering building, where the center of geospatial technologies, where I'm heading that center. It's located in this beautiful building. This is our center. We have master students. We offer MTech and MSc in remote sensing and PG diploma. We have some international students, and they enjoy working. We enjoy working with them, and that's it. So we are open now for interaction.
So, dear participant, as sir said, this session is now open for discussion. So, you can ask him question. So, there was a question from one of the participant. Was a text to me. I will read it on their behalf.
Sure.
Okay. So, the question is, I don't know the name because it is in the WhatsApp group. Okay.
That's fine. That's fine.
How we can separate same crop of a different species like basmati rice and another species? I repeat question.
Sure.
How can we separate same crop of a different species like basmati rice and other species? Is it possible that we can estimate the yield of crops? These are the questions asked by one of the participants.
Okay, so I mean, again, you all are first of all, I think you have very good knowledge, and the types of questions that I can see it's really good. Okay, and I think I can see in the chat. This question is being asked from Savan Graph. Okay, how we can separate same crop of different species like basmati rice and another species. Okay, uh, again, it's a very thoughtful question, and since we have technology, since we are working on this technology where it uses this one term, it's called spectral signatures. Okay, a spectral signature is something like our fingerprints. Our fingerprints are unique. Every person is having a unique fingerprint. Similarly, every crop or every species is having a unique spectral signature. Now it depends on the sensor that we are using, whether that sensor can differentiate between the spectral signatures. Yes, it is possible. It has been done, and normally the technique that we use or the data type that we use to separate these species of same crop, we need information at the individual, not bands level, but within bands. Okay, and that's called hyperspectral imagery or hyperspectral remote sensing. So when we use hyperspectral data, so for example, I was again and again talking about one single band called near infrared band or a thermal band. So when we split that one single band into small bands, it becomes hyperspectral data, and these small bands will be sensitive to the species. Okay, so that's the first part of the question, and the second part is Yes, we can estimate the yield of the crop, because yield of the crop depends obviously on something called photosynthesis, and this photosynthesis, it's a, it's a biophysical biochemical reaction that's going on, and we can get some measurements, or we can get a measure of these process through vegetation indices like NDVI, and through NDVI we can estimate the yield. So that's doable. There are several papers, research paper on this topic and on this technology.
Yes, any more
So
questions?
let me check in the chat section also. I think there was.
Yes, yes, yes.
Hello, sir. Hello.
Yes, yes.
Hello.
Hello. Hello, you can
Is
ask.
it possible? Is it possible to assess the nutrition of soil through the remote sensing?
Nutrients of the soil, nutritional status.
Nutrient. Yes.
Uh, Lal sir, Mr. Amol is asking a question whether it is possible to. Hello, sir. Okay, 1 minute, sir. Sir, you are in. Hello, sir.
Sir has muted their mic.
Lal sir, your mic is off.
Yeah, yeah. Can you hear me now? Okay, great.
Okay, sir. So Amol sir has asked a question that how can we estimate, means get the information about the soil nutrients from the remotely sensed data, or nutrient quality at least.
See, that's I mean, see, remote sensing technique is, it's an indirect technique. It's not doing a direct measurement. Okay, so we would need a certain type of calibration. What calibration mean is, the information that we get through remote sensing is just the reflectivity, okay, or the emitted radiations, okay, in terms of energy values, let's say, okay, or in terms of reflectance, okay, and we need to calibrate it in different areas. For example, if you're talking about uh, soil nutrients, okay, we need to consider there are various parameters where we are looking at. Are we looking at just the top layer, okay, or we are looking at depth, or we are looking at crop root zone depth, okay. So based on that, we need to select a sensor, that whether the sensor is looking at just the top layer of the soil, or whether it can go inside the soil. And once we have selected that sensor, we need to calibrate it. I mean, there is again no direct measurement soil nutrient. There is no direct measurements. You have to calibrate. So yes, it's doable. And by calibration, what I mean is that you take data from satellite image, take your soil samples, measure the nutrients, different quantities or qualities of nutrient, do a quantitative or qualitative analysis, and then calibrate with the spectral signatures of the satellite image, okay, or the data that you are using. And you can get basically a correlation. And in those correlation, then you can again go to another site and see whether that correlation is working. So it's an indirect science. You have to calibrate it first, okay. Once you have calibrated, then you can use it, okay. I can see a question from Mr. Chatur. This is which GIS software is best for LULC change detection? Now, see, I mean, LULC change detection is an image processing thing, and then all the softwares, whether if it's a GIS software or imaging software, um, those are grouped into two groups major. One is free to use or open source, or another one is paid. The paid one, which is one of the best software that I use, is Iridas Imagine. Okay, and the freeware, normally we would use QGIS. QGIS is a very popular software. Okay, so those two softwares, if you have any one of those, that will be good. And let me see if I can see check more questions. I don't see in the chat section, but again, if you want to ask, you can type or you can speak, whichever way you like.
Hello, good morning, sir.
Yes, good morning.
Sir, actually, my research is in AI and agriculture. So, actually, I want the satellite imagery for particular farms. So, how can I get it?
Okay. Okay. Have you visited any website for satellite images, or you are still searching? Do you know any website for that?
No, sir. Actually, I have searched Bhuvan portal and
Okay.
NRSC. I think
NRSC. Okay. Okay.
yes, yes. Huh. So I think, but I don't know the exact way of capturing those images. Should I
Okay.
go
Good.
for the, should I go for the paid product, or can I go for the, what you can say, free images which I can get as a researcher?
Okay. See, most
Yes.
of the data are free for research purposes. So the Bhuvan and NRSC is our Indian websites, and we can get Indian satellite data. Um, but how to search depends. Basically, it will give you an option like which satellite do you want? Okay, would you like to have?
Okay.
And the satellite data will depend on how small or how big your fields are. Okay. For
Okay.
example, Landsat satellite, which is very most commonly used. Okay, it has a 30-meter resolution. So one pixel will will not cover less than 30-meter by 30-meter area. Okay. So if your field is more than 30 meter into 30 meter or 900 square meter area, then you can use Landsat. If it's smaller, then you have to use a finer resolution. Maybe you can take our Indian satellite data, which is resource set, which can be almost at 5.4 meter resolution. You can take that. But what happens is that wherever your fields are, you go to Google Earth, okay, and you just see their latitude and longitude. Okay, just take a bigger area. Okay, for example, if you have four fields, take the four corners or two corners at least of latitude and longitude, and you put that information in any of the website which are giving you free images. So free images you can get is from Landsat. Okay, if you type Google in Google Landsat images, you will get the website. Then you can also get from our Bhuvan website our Indian data, and then there is also a European data. Okay, Sentinel, which is called Sentinel, Sentinel, Sentinel. Okay,
Yes.
that
Mm.
yeah, that's at 10 meter. That's also free. That's 10-meter resolution. So whenever you go on their website, they'll ask two things, two or three things. One is the area. So area you have to give them in terms of either a shapefile or latitude and longitude. Okay, you can
Okay.
give that. Second, they will ask which satellite you want to use. Okay, and
Okay.
what resolution. Okay, so these three information you need to give and you will get. Okay.
Okay, so this resolution will be determined. I mean, see, just now, sir asked regarding the soil nutrients.
Mhm.
So, if we were to measure, I think you had given that answer. But can you repeat what kind of resolution we can use for measuring the soil nutrients? You talked about the sensor, right, sir?
Yes.
We have to use a particular sensor through which I can take the top layer and the depth of the layer. So
Mhm.
regarding the resolution, what I can say?
Regarding the resolution, if we are talking about that, like soil nutrients, so obviously we would like to have a representative area. Okay, for example, uh, satellites, the normal free satellite imagery that we get, it has resolution starting from like Indian satellite have 5.4 meter resolution. Then uh, another free satellite images is from Sentinel. It has 10-meter resolution. Then the next is Landsat, which has 30 meter. So, I think the final resolution is better. Maybe 5.4 will be
Yes.
better. But again, when we are talking about soil nutrient, we have to also see which type of satellite we are seeing, because all these satellites are just seeing the top layer. They are not going beyond the top layer. Okay. So
Okay.
for that we may need microwave data. Okay.
Microwave data.
Yeah. When we are going beyond the top surface, where we are going
Correct.
subsurface.
Correct.
Okay.
Okay, sir. Thank you so much. Thank you.
Great. I can see another question from Dr. Amol Jarak. How can we distinguish between rangelands and dry farming areas, both having low NDVI values? Okay. Um, Again, that's a good question, because we are bound to see overlaps in NDVI ranges. Okay. Uh, but rangeland and dry farming areas, rangeland probably will change their NDVI values after, maybe during different seasons. Dry farming area may remain constant. They are not changing NDVI values uh, like consistently. They may have, uniform NDVI values. So when you are seeing changes, then they could be rangeland. There could be another way. It's still, we are not able to figure out it. Again, there are different tools that we can use. You can also use a classification method, okay, where we can classify these classes using a different bands, because NDVI is using only two bands, which is near infrared and red. Okay, so these two bands may not have enough information to separate between rangeland and dry farming areas. So we can use more bands, and what we can do is we can classify based on some ground measurement. We can say, okay, if the spectral signature falls between this limit, rangelands. Otherwise, put it in dry farming areas. So that we can do, and through that, at least we can get an idea where the rangelands are, where the dry farming areas are. Okay, so two ways. One is watch the NDVI throughout the season of rangelands and dry farming areas, and see which area is changing NDVIs over the time. Okay, because one of these areas will almost remain constant throughout the growing season. Okay, this is one thing. Second thing is use a classification method. Okay, classify images using more bands, and then you can get these land use classes differently. Differentiate. We can differentiate between land use classes. Okay.
Uh, okay, participants, thanks for having interaction with sir. And I'm also thankful to Dr. Deepak Lal sir for sharing his ideas, thoughts, the fundamental concepts he has also elaborated, and also discussed about the applications of GIS and remote sensing in the field of agriculture in the climate change scenario. So if there is any question you can ask, otherwise we'll be closing this session now. So on behalf of Department of Geography, the colleagues of my department, Marutabai Chogle College of Arts and Science, Autonomous, and the AICT Atal Academy, I propose my vote of thanks to Dr. Deepak Lal sir for sharing his views, thoughts, ideas, and answering questions of our participants. Thank you, sir. Thank you for being with us and giving your valuable time. Thank you, sir.
Thank you. Thank you very much, Dr. Gaikwad and the rest of the team. I also appreciate all the participants. They were very patient throughout this 2 hours. I know it's a long session, but it's all interesting, and I hope it was useful for you. And again, whatever I have talked, if you have more questions, you can always email me. Otherwise, there are several research paper on all these things. I've chosen a topic where you can find things. It's not hidden anywhere. You can find things on in the research community everywhere. You can see all the information that you would like to see. So thank you very much. Stay safe. Follow social distancing and all the COVID norms. And I wish you all the very best in your future works and in your future endeavors.
Okay. For the information of participants, I have kept every resource person's contact details, their profile on our Google Classroom. So you can access through it. And I think sir's profile is available on their institute also, as well as even if you check into Google Scholar, it's available. So again, thank you for showing your interest in helping, and our participants also are willing to have interaction with you online and by mail and chat. Thank you, sir. Thank you for being with us once again. And thanks for the participants for being there patiently for so long session. Thank you, sir.
Thank you.